Hello. I will be covering topics like heat sources, meter. I will be inserting a thermometer. I will be inserting a thermometer like this, and the bulb is like this, and the temperature of the thermometer is denoted as L, and this is the length of the thermometer L, and this is I'm denoting as D. This I'm denoting as D. Okay, and this is thermometer, and it is having some gas or filled with some fluid here like this. Okay, it's filled with fluid like this. Now the fluid is flowing, and then this fluid has got in contact with this well, and into the well I have inserted into this. Okay, now here, if the temperature of fluid, it is supposed to be T infinity, the temperature measured by the thermometer not be the temperature measured by the thermometer will not be T infinity, but that at the end, due to transfer of heat by conduction along the packet wall, due to transfer of heat along the packet wall from its bottom to its top, the temperature we found is this one, TL. Then this is called as a error estimation case. In that case, what we do is nothing but, as per the case what we discussed earlier, we can write it as theta by theta 0 is equals to cos h m into L minus x divided by cos HML. Okay, cos HML. This is the case we have discussed already in our earlier classes. Okay, means it is considered as a kind of a pin fin. This thermometer I have considered as a kind of a pin fin protruding from the pipe wall, and assuming that there is no heat transfer from the pin tip, then the temperature distribution theta is equals to theta 0 cos HML m into L minus x divided by cos HML. And now if I want to find out the temperature distribution at x is equals to L, then the temperature what I found is TL. Therefore I can say this is equals to theta L by theta 0 is equals to T by T infinity. Theta 0 is equals to T0 minus T infinity is equals to this TL, right? This is equals to cos h m into L minus L divided by cos HML. Okay, means that is equals to 1 by cos HML, right? Means obviously here theta L by theta by theta 0 is equals to 1 by cos HML. Okay, so this ML should be as large as possible. Why? Because M is equal to HP by Ka. We know that M is equal to HP by the square root of M square is equal to HP by Ka. M is equal to square root of HP by Ka. Right? And we know cos HML is equals to in this case, if ML is in this case, if ML is trying to be very large, we need to consider ML should be as large as possible to be large. Then when ML is to be large, H should be very large. it should be very large so that you can get a error estimation in a error would be in a small values. Okay, this is something like we need to do it in case of error estimation problems. Okay, right, this is a temperature T infinity. I'll write it here T0. This is T0, and this temperature of the fluid which is in contact, this is TL, and this is T infinity. Since this fluid is in contact with this wall of the well wherein you are putting thermometer, so this is exposed to TL infinity and it is connected to T0, there is a chance of the heat dissipation. Due to that, the temperature is going to be TL. Now this has to be closer to the T infinity in order to achieve the H. In order to achieve this TL as closer to this T infinity, we should have ml should be as large as possible. So ml should be as large as possible. For that ml to be as large as possible, what you have to do is nothing but either H should be in this. If I write m is equals to square root of HPLA, in that H should be as large, should be large value, or otherwise K should be very small value, so that I can reduce this. H should be as large, or otherwise, so that I can reduce this conductivity here, and then I can ensure a closer values of the fluid temperature. This is what I mean to say here. Okay. Now suppose in the case if this L, which I have stated here, this L is larger than the dia of the tube, this dia of the tube. Okay, this dia of the tube. In that cases, what you have to do is nothing but you cannot protrude you cannot insert the thermometer into the tube in the tube. So in that case, you need to make this okay tube well into which you are inserting your thermometer to be obliquely constructed, and it is to be welded like this, and then you can put your thermometer like this. Okay, you put your thermometer like this. Okay, and this is going to be the length, whatever the length you wanted to put L, right? So this is the length. Okay, like that you can do the corrections, and then you can achieve the error estimations in temperature measurements. Okay, so this you can make use of this formula. Okay, in temperature error in temperature step. Okay. Okay, so this could be means what temperature measurement. The temperature thermometer can be estimated by fin theory. The fin theory is what is that? If it is assumed this fin as a insulated tip end, then in that case temperature distribution theta is equals theta 0 cos hm L minus x by cos hm L, and for at x is equal to L, if this is the length considered x is equal to L, and the other end is insulated, then it is equals to theta L by theta 0 is TL minus T0 by T0 minus T0, and this is equals to cos m into L minus L is equal to 0 1, this is equals to cos 0 1 1 by cos HML, and this to be as large as possible, therefore 1 by as large as possible, therefore this to have this value. Okay, now H should be as large as should be large, or K should be small. With the help of this I can reduce the value ml like this. Okay, no, right, this is about error temperature measurement. With this I will go to the next topic called the systems with heat sources. Right, that I am taking today, the system with heat generations. Okay, now this application is for one dimensional steady flow steady flow conduction cases only. The application is going to be one dimensional steady state conductions only. I am talking about heat generations. Okay, now the topics I will be covering in this class is going to be the plane wall with internal heat generation and hollow cylinder with internal heat generation. Okay, right, before going into this cases to deal with, now let me introduce why do you giving so much importance in this case is nothing but there are many instances wherein there is a heat absorption and heat generation will take place. For example, like in internal combustion engines where heat energy is generated within the system only. Okay, and similarly in nuclear reactor also, the due to nuclear fission there is energy is going to generated in the system only. Okay, similarly wherever the combustion and chemical reactions do take place, those are generated within the system only. And again, and the second case and another case is nothing but in case of civil people, the drying and setting of concrete is also while drying and setting and setting of the concrete, there is a kind of some kind of a heat generation would takes place. And similarly, in the electrical conductors also, there is some kind of a heat generation you can take place. So in all these cases, in all these cases means what, either the case of either the case of nuclear reactor nuclear reactor where enormous heat is going to be released by nuclear fission, or otherwise in IC engine where the piston cone is subjected to high temperatures. Piston cone is subjected to high temperatures due to internal combustion, and again setting of concrete and chemical reactions. During chemical reactions, okay, during chemical reactions, the heat is going to be generated. This heat to be dissipated out, or otherwise, it is very important to know the temperature distribution within the system itself. So, keeping in this view, in case, I am trying to derive simple cases of heat generation along with conduction. How the temperature distribution would be, that I am trying to talk about today's class. Okay, so here the absorption generation within the body is denoted by, here the heat absorption or generation within the body is denoted by q dot. The unit of this is going to be watt per meter cube. Means what, the heat generated per unit time per unit volume is denoted as q dot, right? And along with there is a heat conduction also, that I will take into consideration. Okay, so first I will take the case of plane wall with internal heat generation. First case I am trying it here, plane wall with internal heat generation. Case I am trying to take here now. Okay, now plane wall means what, I am let us consider a slab of thickness L. I am taking a slab of thickness L. I am draw the sketch, relevant sketch for this. Let us take a slab of thickness L. I am taking a slab of thickness L. Okay, in the region of in the region 0 is less than or equals to x is less to L. Okay, and it is of uniform thermal conductivity. This slab has got uniform thermal conductivity. Okay, so this has got uniform thermal conductivity. I have taken a plain slab of length L, and the range of this slab is going to be 0 is less than or equals to x, means that x is greater than or equals to 0, and L is greater than or equals to x, means that 0 is less than or equals to x, and x is less than or equals to L. This is the region I have considered. Okay, and it's of uniform thermal conductivity. The slab is of having uniform thermal conductivity. And conductivity. Let an electric current pass through the slab, causing a heat generation of Q dash. When electric current passes through the slab, generates a heat denoted as Q dot. it is the unit for this is watt per meter cube. Okay, and this is the description of the slab. What I mean to say, this is a slab length, this is a slab of length L. Okay, this is length L, and here there is electrical current pass through. Due to this, there is a heat generation would take place, and the heat generation is denoted as Q dot watt per meter cube per minute. And the temperatures on the two faces of the slab, this left side face and this is right side face, is TW, and the wall temperature of the wall TW, and this is TW, and the one side of left side wall is the boundary conditions are x is equal to minus L by 2, and the right side wall boundary condition is x is equal to plus L by 2. Okay, and at that center I am taking x is equal to 0, not x is equal to 0. Okay, now okay, now it is defined in such a way that the temperature at either side of the slab is taken as a TW. Therefore, it losses it means what, the either side of the wall it dissipates the same amount of heat by convection only. Here also the heat loss by convection is same. Also this side also heat loss by convection is also same. Okay, and two sides will be same. Okay, now this is the description of the case I have taken it, and again. Now I am considering an element in this slab. I am considering an element here. This is I am considering an element. Okay, this is an element of thickness dx. This is thickness I have considered. This element has got a thickness dx. Okay, thickness dx, and cross sectional area as usual. This is say cross sectional area say A. Cross sectional area say A. Now at this point heat is conducted at x distance is, now I will change the here, the heat conducted through the slab is to this elemental is Qx, and the heat going out of the slab is at this elemental is denoted as Qx plus dx, and similarly heat generation at this elemental area it is denoted as Qg. There is a heat generated at this elemental area Qg. Then it is denoted as heat generated is denoted Qg. This heat generated Qg is I'm writing as Qg is equals to heat generated within the elemental slab Qg is equals to elemental slab Qg is equals to, this is denoted as Qg is equals to, I have denoted already Q dot, this is the heat which is generated per unit volume into area of the slab already is denoted as A, and the length is going to be dx. Okay, this is okay. Now heat generated within the slab within the small elemental area is Qg is equals to Q dot A dx. Now okay, now if I go to that energy balance, if I go for the energy balance in this slab, energy balance in the dx element, okay, this is equals to heat passing through the slab is at x is Qx, and heat generated is Qg, and leaving the slab is equal to Q plus Qx plus dx. Okay, and we know how to write Qx, how to write Qx plus dx. Therefore, I am straight away writing this minus Qx is equal to minus by conduction. Therefore, Ka dt by dx, since it is a one dimension, and qg is equals to q dot a dx is equals to minus ka dt by dx, right, minus ka into d square t by dx square into dx. Okay, right? So now here minus ka dt by dx minus ka dt by dx, as I said, it gets cancelled. Now the remains is, the remaining is qa q dot a dx is equals to minus ka d square t by dx square into dx. Therefore dx also gets cancelled, and a also get cancelled. Now this is going to be, d square, okay, sorry, okay. Now this is this one. Now I am going to the slide. This is equals to this becomes, this is turned out to be d square t by dx square into q dot plus q dot k is equals to 0. This is equation number 1 I am denoting as, okay, right? So this is equation number 1. However, this already we have proved, proved that the three-dimensional Cartesian heat conduction equation, we already derived. What is that? Dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q dot by k is equals to 1 by alpha into dou t by dou t. We have already derived. Now there is no steady state, therefore this is 0, and it is a single one dimension, therefore y and z are also 0. Means what? This is equals to, in a one dimension it is going to be the variation is only one x direction, therefore d square t by dx square plus q dot by k is equals to 0, right? The same equation I have simply brought down that fundamental concepts which we have already aware of it. From that I have brought this form. Okay, I have brought this form. Okay, this and this are same. Now once we know this is uh, taken, okay, now we'll try to fix the boundary conditions here, right? So now when we first integrate this equation, this one equation one, okay, first I will integrate this equation first. Once I will integrate the equation, then this equation becomes dt by dx, integral of d square t by dx square into dx plus q integral q dot k dx, like that. Okay, is equals to, it will become dt by dx is equals to, if q goes other side, it becomes q minus q dot by k, and integration of this one is equals to x, and there is a constant c1. Okay, and similarly again if I integrate this equation 2, then it becomes t is equals to minus q dot x square by 2 into k plus c1x plus c2. This is equation number 3. Now once you know these equations, right, now I will try to find out the boundary conditions for it. Okay, since here already, if you see the diagram, here, t is equals to tw here at x is equals to minus L by 2, and t is equals to w at x is equals to L by 2, means this is the temperature distribution about the center line is symmetrical. Now under steady state conditions, here if you see these are all under steady state conditions, the heat generated within the body must be convected away from the surfaces of the slab, okay, symmetrically, or otherwise simply I'll say, I'll repeat once again. Since TW is T is equals to TW at x is equals to minus L by 2, and T is equals to TW at x is equals to plus 1 by 2, means the system, the temperature distribution is uniform, the symmetrical at the center, means I can draw this diagram like this, and the temperature would be maximum at the center only, and the temperature would be maximum occurs at the center only, and whatever the heat, if you want to dissipate it from this system, half will be towards left side and half will be towards right side. Therefore, with this analysis, now I'll fix up my boundary conditions like this. At x is equals to, I'm fixing boundary conditions at x is equals to 0, dt by dx is also 0. Okay, means you can check it here. At x is equals to 0, here dt by dx is also 0. Okay, now dt by dx is equals to 0. And the next one, as I said, since the temperature distribution about the center plane of the wall is symmetrical, therefore you can experience maximum temperature at the center, and whatever the heat it is generated, it will be distributed off towards left side and off towards right side. Means therefore I can say here, that is the heat by conduction, I can say that is Ka dt by dx at x is equals to minus L by 2 is equals to Ka dt by dx at x is equals to plus L by 2 is going to be half into, it is convected to that, so outside here you can see here, it is convected out here, you can see here it is converting out. Therefore I can write it here, the heat generated is Q, right? Half of the heat generated is Q, half Q by 2 into A into L. Okay, this is second boundary condition. Alright, this is second boundary condition, this is first boundary condition. Okay, got it? Now this is the equations. What are these equations? These are the equations, right? Now using, I'll write it here only because it is I should refer these points, therefore I'll write it here only. Using boundary conditions, condition 1, when I use boundary condition 1 in equation 2, means what? Dt by dx is equals to here, this is equals to dt by dx is equals to 0, and q dot by minus q dot by k into x is also 0 plus C1, right? Therefore C1 is equals to 0. When I use boundary condition, C1 is equals to 0. Therefore the temperature equation T is equals to, minus Q by K into x square by 2 plus C1 is 0 plus C2, right? This equation, when the first boundary conditions are used, this is the equation will come. Okay, now if I, now in this equation I use x is equals to L by 2, at x is equals to L by 2, if I use it, then when x is equals to L by 2, the boundary condition when x is equals to L by 2, T is equals to TW, therefore TW TW is equals to minus Q by K, and L is equals to X is equals to L by 2, therefore this is equals to L square by 4 into 2 plus C2, right, plus C2, okay, therefore this is equals to Q dot L square by 4 to the 8, 8K plus C2, okay, 4K C2, okay. Now C2 is equals to, C2 would become, C2 is equals to this minus, right, C2 is equals to TW plus Q dot L square by 8K, okay, Q dot L square by LK. So now with the given two boundary conditions, I could find C1 and C2. Now substitute C1 and C2 in the equation of general equation of temperature distribution. Here T is equals to T is equals to the general equation is T is equals to, if I substitute here, now T is equals to minus 1 by 2 Q dot by K x square plus C1 x is equals to 0 and C2 is equals to TW plus 1 by 8 Q dot by K into x, that is, what is that value here, you have got it, let me check. This is equals to L square, therefore L square, okay. Now therefore T is equals to, I can write TW, I'll take it out here, TW, and here Q dot by K 8, I will take it out, Q dot by 8K I am taking out, then it becomes, this is L square, only remains is L square, minus here 2 only is there, but here 8 I have taken, therefore this is going to be 4x square. Okay, this is equation number 4. Okay, this is equation number 4. Got it? Now, so means what? Now, if I want to find out the maximum temperature, suppose if I was asked to find out the maximum temperature, and I already know that the maximum temperature would be finding at x is equal to 0. Therefore, this interest T max is equals to TW plus Q dot by 8K into maximum at x is equal to 0 is equal to L square. Therefore, the maximum temperature is TW plus Q dot L square divided by 8K. This is maximum temperature. You are going to get it. Okay. This is equation number 1. Okay. Now, if I want to calculate heat flow rate. Okay. Now, if I was asked to calculate heat flow, what is that heat flow? Will define as Q. Heat flow is defined as Q. Q is equals to minus Ka dt by dx. I know, and Ka minus dt by dx, I know. This is equals to, at x is equals to L by 2. Is already have told that this is going to be of Q dot AL, that is equals to of Q dot AL. Then this is equals to, I can write it as in this form, this one. Okay, this is equals to, I'll write it as minus Ka. Now I go back to that equation. Here dt by dx is equals to, here you can see dt by dx is equals to q by k x, right? So I'll write this equation. Okay, now I'll write it minus ka into minus q by k into at q by, here what is mentioned is, you just check it, right, at x is equals to L, this is equals to q by k into L is L by 2, therefore q by k into q by k L by 2, and I can use here 8 and I can use it here 8. Okay, So this is equals to, when it gets cancelled, 8 gets cancelled. Therefore, this is equals to Q by K. This is equals to, and the K is there. This K or this K also gets cancelled. This is equals to of Q dot AL. Okay, right? This is the form you are going to get it. This is the form you are going to get it. Okay, right? So means if heat transfer is, if I want to calculate it, this is equals to Q is equals to minus K dt by dx at x is equals to L by 2, and dt by dx at x is equals to L by 2 is equals to, I have mentioned here, the temperature distribution K minus Ka dt by dx at x is equals to A is equals to, from the first equation which I derived earlier. From that I substituted q by k L, x, q by k x, that is equal to x is equal to L by 2, and I put here 8 so that I'll try to bring into a form of QAL, right? That I have mentioned here. Okay, right? Now, so this is one equation. If next case is, if the ambient temperature, now if the ambient temperature is T infinity, in the case here, the ambient temperature is T infinity, right? Here also T infinity. With the ambient temperature is T infinity, and the heat transfer coefficient, heat transfer coefficient is H. Heat transfer coefficient is H. Then at phase x is equal to L by 2. Means here at phase x is equal to L by 2. At this phase x is equal to L by 2. We write Q is equal to, heat conducted is equal to, Q is equal to of, as I said, both sides it is going to be of Q dot AL. This is convected out thoroughly. Whatever that heat it is dissipated from the slab is to be convected by fluid. Therefore, this is equals to, fluid has got a coefficient, heat transfer coefficient H, and area is also A, and the temperature difference are, from the wall it is TW, and it is infinity. This is fluid temperature is infinity. There it is equals to A gets cancelled, and this is equals to, and A gets cancelled. Now this is equals to TW is equals to, now I am trying to brought it into form. TW is equals to, this is equal, see here it is Q by 2 as it is there, Q dot by 2 as it is there, and H will come here. Therefore H, okay, right? And L is already there. Q by 2 L, Q by 2 QL by 2H plus, and T infinity, if it comes here, it is going to be T infinity. Okay, means I mean to say, or I write it as TW is equals to T infinity plus Q dot L by 2H. This is equation number 6. Okay, now if you substitute this 6 in equation number, if you substitute this equation 6 in equation number 4, equation number 4 is this one, right? TW. How the equations turned out to be, I will talk about it, right? The equation 4, what is the equation 4 it talks about is nothing but T is equals to TW plus Q dot L square by 8K, and we have found here TW is equals to T infinity plus Q dot H by 2 Q dot L by, sorry, this is Q dot, this is Q dot L by 2H, that I am substituting here, right? So this is equals to T infinity plus Q dot L by 2H plus Q dot L square by Q dot L square by 8K. Okay. Therefore, this equation can be, let me check. Okay, right. This is equal to fourth equation. Sorry, this fourth equation. This is not the fourth equation. Q dot by L into L square minus 4x square. Okay, this is equation, right? So this is equals to L square minus 4x square. Okay. Now the temperature distribution is this one. Okay. Okay. So means T is equals to fluids surrounding fluid temperature T infinity and the Q dot L by 2H plus Q dot by 8K into L square minus 4H square. Now this is keep in mind. Now I will be discussing about the effect of Biot number on temperature distribution in a slab with heat generation. I will talk about. Okay, right? So this I am talking about it. Now I will take this effect. I'll note down this one and I'll take that sketch here, right? And the temperature distribution just now the effect of Biot number on temperature distribution on a slab with heat generation I am discussing about. That is final equation is equals to T is equals to T infinity plus Q dot L by 2K plus Q dot by 8K into L square minus 4x square. This is the equation, final equation, and I denoted as number 7. Now, this I'll try to talk about effect of Biot number on this temperature distribution. I want to talk about. Now, what is the Biot number? First, we should know. All right, the Biot number is defined as HL by K. Right, the Biot number is defined as HL by K. Let I am denoting as 1. Okay, it is a dimensionless number. It is compares it is Biot number is defined as HL by K. It is a dimensional number. It compares the heat transfer coefficient with internal conductance of a slab. This Biot number is going to compare the heat transfer coefficient with internal conductance of a slab. Okay, and I can define as it is the ratio of it is defined as Biot number is defined as the ratio of conductive resistance to the resistance to the convective resistance. Convective resistance. Right. Means conductive resistance is equal to L by K into convective resistance. It is HL by K. This is nothing but okay. Or simply I can say it is the ratio of the conductivity to the convective resistance of a slab. Okay, it is defined as the ratio of conductive to convective resistance of a slab. It is defined by HL by Ka. All right. Now this once you know this one, Biot number is equals to conductive resistance by convective resistance. Once you know this now I am considering again a slab which is in the region of 0 is less than L, 0 is less than X and X is less than or equals to L with internal heat generation Q dot. The phase at X is equals to 0. The phase which is at X is equals to 0 is maintained at a temperature of T0, whereas the phase at X sorry I'll write it here. phase at x is equal to 0 is denoted as T is equal to T0, and phase at x is equal to L dissipates heat by convection to the surrounding at is T is equal to T infinity. At T is equals to I can say TL, which is at x is equal to L, the temperature is going to vary, from which it is trying to dissipate the heat to the surrounding TL, which is maintaining temperature of TL, and outer and above all the heat transfer coefficient is defined as H. So this is the I wanted to describe the effect of Biot number in case of a temperature distribution of a slab when heat generation is considered. Okay, right? Now this problem I will be finding out in a way. I'll try to write the problem here. Now the problem means whatever the problem I am formulating is like this. For the case d square T by dx plus q dot by k is equal to 0. This is, I know already, a slab with heat generation, which is which is considered for a region of 0 is less than or equals to x is less than or equals to L. This is I am denoting as condition 1, and when T is equals to T0 happens, T is equals to T0 happens when x is equals to 0 and minus Ka dt by dx, right, at x is equals to L would be h into t minus t infinity, ha into t minus t infinity. A will get cancelled. This is equals to minus k dt by dx is equals to h into t minus t infinity. Okay, right? So this is t is equals to t0 and at x is equal to 0, and this I am denoting as minus k dt by dx is equal to h into t minus t infinity as denoting as 3 at when t is x is equal to L. Okay, now this equation I am writing it as k, whatever I mentioned is k dt by dx plus h into t minus t infinity. In that h of t into t minus t infinity, I will bring ht to this value to here. Ht is equals to ht infinity. Okay, at is equals to L. Okay, so the solution of this problem, I am evaluating by finding C1 and C2 constants. C1 and C2 constants. Okay. Now we know that dt by dx is equals to q dot by k into x plus C1. Already it is there in earlier we have derived. This is C1. Okay, and also we know that T is equals to we derived in this session only. T is equals to minus of q x square by k plus C1x plus C2x. I mean to say this is nothing but, if this is the equation, if I integrate it first, what will happen? If I integrate again twice, what will happen? You know, right? So that is going to be temperatures, right? So this is you have got it. Okay, these are the two equations you have got it. Now to these equations, I'll apply boundary conditions, right? The boundary conditions are, right, first boundary condition 1. What is boundary condition 1? Small one, letter 1. This x is of boundary condition is this one. I am trying to apply it, right? So this is equals to, when I apply the boundary condition x is equals to 0, when I apply x is equals to 0 to this one, this is equals to this is the temperature equation, right? To this temperature equation, when x is equals to 0 applied, when x is equals to 0, the boundary condition T would become T0. Therefore, T0 is equals to minus of Q dot x square is 0 by K plus C1 into 0 plus C2. Therefore, C2 is equals to T0. Right? This one the boundary condition x is equals to 0 I applied. Then okay, C2 is equals to 0. Then and again dt by dx, here dt by dx is there. Dt by dx is equals to minus q dot k by x plus c1 is there, right? Therefore, in this equation k in this equation k into dt by dx, in place of this dt by dx I'll be using this one minus q by k into x plus c1 is q dot plus h into t is, this is the equation, that is equal to minus of q x square by q dot x square by k plus c1x plus c2 is there, c2 is equal to t0 is equal to ht naught, ht infinity, right? Now this is equals to c1 of k plus hl is equals to ht infinity plus ht infinity plus k q dot by k into L plus h by 2 q dot by k L square minus ht0, you are going to get it, okay? And similarly c1 is equals to h into t infinity minus t0, right? H into t infinity minus t0 divided by h into 1 plus k by hl into L, here I am taking it here, plus q dot L by 2k into 2k plus hl divided by 1 plus k by hl into hl, alright? Now this h and this h gets cancelled and c1 becomes, c1 is equal to, I'll write it in a big way, c1 is equals to t infinity minus t0 divided by 1 plus k by hl into L plus 1 plus 2k by hl divided by 1 plus k by hl, right? So now substituting the c1 and c2 is equals to t2, the general equation, what is the general equation? The temperature general equation is t is equals to minus of q dot by k x square plus c1 x plus c2. In that, if I substitute c1 and c2 in the equation, then t is equals to general, the t is equals to, I'll write it here, t is equals to minus of q dot by k into x square plus c1 is equals to t infinity minus t0 divided by 1 plus k by hl of L plus 1 by 2k by hl of 1 plus khl, okay, into c1x plus c2 is t0, right? Now I'll write it as this t temperature distribution means a temperature at any point x, I can say tx minus t0 is equals to, I'll write it as I will write in a fashion. See here, I will write it. First, I will write it like this: minus 1 by 2 q dot by x square q dot by k x square into x square plus t infinity minus t0 divided by 1 plus HL by k is equals to Biot number, and again k by HL is equals to 1 by Biot number, 1 by Biot number into L. This is x is there plus 1 plus HL by k is Biot number, means 2 by Biot number, 2 by Biot number into x divided by 1 by this is also HL by k, therefore 1 by Biot number on the Biot number. Okay, so this is something you are going to get it. Now this again I am simplifying in this way. This is equals to t infinity minus t0 by 1 plus Biot number, sorry, t infinity plus t, in, t infinity minus t0 divided by 1 plus 1 by Biot number of x by L plus q dot by 2 k L square, right? I take it out. Now this is equals to 1 plus 2 by Biot number into 1 plus 1 by Biot number, right? Here this you just observe this one. This is equals to x by L. This becomes, means when x by L becomes L gets cancelled. Okay, L would be there, and this remains there. Then minus x by L whole square. Okay, so this is the equation you are going to get it. Now with these assumptions, now if I take the heat flux, what is that heat flux? Q by A dt by dx, right? Dt by dx already know at x is equals to 0. This is called as a heat flux Q at x is equals to 0. This is equals to k minus k dt by dx at x is equals to 0, right? And dt by dx is equals to, you can see here, dt by dx is equals to c1, therefore c1 that is equals to minus c1 k, right? C1 k. Why? Because here I will write it here. How you have got is nothing but, since already I have defined dt by dx is equals to minus q by k, q dot by k into x plus c1, right? And when x is equals to 0, this is equals to 0, dt by dx is equals to c1, therefore this is c1 k, right? Okay, now then this is equals to minus k into t infinity minus t0 divided by 1 plus 1 by Biot number into L can be written as L can be written as Q dot L by 2k into k into 1 plus 2 by Biot number divided by 1 plus 1 by Biot number that is equals to minus k by L. I'll go back once again here. This is x is equals to 0. When x is equals to 0, this is the form I am trying to bring it. Okay, t infinity minus t0 1 plus Biot number by x is this is equals to this is equals to, I'm trying to draw it in this fashion. Okay, now this is equals to minus k by L, t infinity minus t0 divided by 1 plus by 1 by Biot number minus q dot L by 2, k gets cancelled. This is equals to 1 plus 2 by beta Biot number divided by 1 plus 1 by Biot number. This is equation number 3 I am denoting. Let us now examine two special cases. Two special cases I am talking here. Two special cases. Okay. So I know there is some confusion here. I'll try to talk about those confusions. Right. I'll discuss. I'll go back one by one. Here I'll talk about it. Right. Okay. So where we got it. Okay. One more slide. Yes, this is effect of byte number. Here, byte number is defined HL by K. Okay, that is okay. And the regions I have selected 0 is less than or equal to x is less than or equal to 0. When x is equal to 0, means when I'll take it here. This is slab, let us take. When x is equal to 0, the temperature is T0. Okay, and x is equal to L. This is length L. The temperature I am considering as T, and it is going to dissipate the surrounding temperature T infinity. Okay, so this is the case. Then d square T by this is generalized uh, one dimensional steady state conduction equation with internal heat generation d square T by dx square plus q dot by k is equal to 0. And when T is equal to 0, x is this I have defined it. And again, the equation for heat Q is equals to whatever the heat it is there is going to be convected out, heat generated is going to be convected out, that is equal to minus Ka dt by dx is equal to h into this T minus T infinity, that is equals to A, when A gets cancelled, this is equals to minus K dt by dx is equal to h into T minus T infinity. This up to here, okay, no doubts. Now when I go to the next the equation K dt by dx plus T I have brought to our left side, minus K becomes means this is going this side, this is also T minus T infinity, therefore T infinity is become positive, and this is going to be the equation turned into this form at x is equals to L, right? At x is equals to L condition. Now we need to find out C1 and C2. To find out C1 and C2, what I have to do is nothing but when I put x is equal to 0 and t is equal to 0 in the equation, in this equation, or the equation, this is equal to 0, this is equal to 0, t is, when x is equal to t becomes t0, therefore C2 is equal to t0. Once I know this t0, now what I will do is the generalized equation k heat, this is the generalized equation at x is equal to L, therefore this is k into dt by dx. Dt by dx I have put dt by dx is equal to the first differential of d square t by dx square plus q dot by k, that first integration I have put it here, minus qx by k plus c1, and again plus h into t, the temperature profile at any point x at any point x is equal to, this is you know, this I have put it here, and is equal to ht infinity, and then from this I have tried to find out C1. This is C1 here, this is only the unknown C1s are there, then in this I have found C1. Alright, once I know C1 and C2, I substituted this in the equation, general temperature equations, like this I substitute general equations, and finally I reduce this form into Biot numbers. Okay, once I reduce it into Biot numbers here, I will try to examine two cases. When Biot number is tends to infinity, when Biot number is equals to 0, what is happens? Okay, these two cases I will try to understand. Right, when Biot number is equals to infinity, when a Biot number tends to infinity, I mean HL by K is infinity. When HL by K is infinity, then what will happen? There is no surface resistance, right? Means anything by 0 is equal to infinity. Therefore, here the K is equal to 0. I mean, this is equal to K is equal to 0. That means the equation will turn to be, right, T of x minus t0 is equals to t infinity minus t0 into x by L plus QL by 2 K QL square. I'll write it once again. I'll take this in another page, right? This is better, okay? I'll take it to another page. I'll write it in another page. All right. Now I'll repeat once again. I'm taking two cases. First case, when Wyatt number is, when first case one I am writing is when Wyatt number tends to 0. This means tends to, sorry, when Wyatt number tends to infinity, h tends to infinity, or a body with no surface resistance, no surface resistance, h tends to infinity, or the body with no surface resistance. The temperature distribution, now the temperature distribution will be obtained by putting Wyatt number is equal to infinity. Wyatt number is equal to infinity. When I put Wyatt number is equal to infinity in the temperature distribution, then what will happen? I'll talk about it. Okay? Now when I put Wyatt number is equals to infinity, Tx minus T0 is equals to T infinity minus T0 into x by L plus Q dot L square by 2K into x by L minus x by L whole square, right? This is the equation when Wyatt number tends to infinity. So how did you get this one is nothing but I will tell you where is the Wyatt number relations I have used here, right? In this Wyatt number equations, Wyatt number is not there, therefore T infinity minus T0 by 1 plus this is there, this is equal to infinity, this is equal to what will happen 1, this will become T infinity minus, is it not, right? You can check it here. This 1 plus 1 by Wyatt number is infinity, 1 by infinity is equal to 1, therefore this is you have got T infinity minus T0 by x by L, you have got it. And then the next term is, you can go to that next term here, Q dot L square by 2K it is there. This is also what will happen, this is equals to 1, this is also 1, therefore x by L minus x by L whole square. This is how I have reduced the effect of Wyatt number on temperature distribution. Okay, now this is first case, right? This is first case. And if heat generation is neglected, then this is equal to 0. Then what will happen? Tx minus T0 is equals to T infinity minus T0. Since it is 0, right? Into this, everything is 0, therefore into x by L. This is same as the equation what you have derived earlier. First cases, steady state heat transfer through a slab. Okay. Now the second case I'm trying to deal here is nothing but when Wyatt number is changed to 0, means what? HL by K is equals to 0. Let us assume that when HL by K is equals to 0, definitely H is equals to 0. It's changed to 0. Means here what will happen is the body with no conductive resistance, right? Here H tends to 0 means a body with no surface resistance. Now here the body with no conductive resistance, right? Now the temperature distribution would be T infinity minus T0 is equals to Q dot L square by 2K into 2 into x by L minus x by L whole square. I'll go back again this to explain this also. Okay. If you go here, right, Wyatt number tends to 0. This is equals to this 1 by 0, right? 1 by 0. Then what will happen? t infinity minus t0 by 1 by 0. This is equals to what is happening is, you can check it here, that is equals to 0, right? Now next, what is that next equation is, if you see here, one more equation is here, right? QL by, this is also 1 plus 2 by Biot number. This is also, what is Biot number is equals to 0, and here 1 plus 1 by Biot number is equals to 0. This is equals to x by L, right? And x by L square. You can check it here. This is becomes this form, okay? And this is the case, second case you are going to deal with, okay? Means now the effect of Biot number on temperature distributions in case you have defined it. Means when Biot number tends to infinity, when Biot number tends to 0, I have defined, okay? So right here, I'll repeat once again. Biot number is Biot number is equal, tends to infinity, means that Biot number is equals to infinity. Then what will happen? No surface resistance. H tends to HL by K, right, is equals to infinity, right? Right here, there is no surface resistance here. There is no surface resistance going to be here, and you have got the equation QL by, you can see here, QL by 2K square into H. Okay, when the next case is nothing but when Biot number is 0, when Biot is equals to 0, HL by K is equals to 0, then in that case H is equals to 0, right? H is equals to 0. When H is equals to 0, means there is no conductive resistance here. H is equal to 0 means this is also 0. There is no conductive resistance here. The temperature distribution in this case is going to be like this: T infinity minus T0 is equal to Q dot L square by 2K into 2x by L minus x by L whole square. Okay. This is the equation, you are going to remember it. Okay. So these are the two cases I am discussing about it. With this, now I am, as time is available to me, I will try to talk about hollow cylinder case. Hollow cylinder with internal heat generation. Internal heat generation. Okay. I'm not going in detail about this in anything now. Now I will try to straight away I will write that equation. Heat conducted through radial wall plus heat generation is equals to QR plus DR. This is there, or otherwise what I can do is nothing but general equation. We know that d by dr of R dt by dr plus q by k is equals to q dot by k is equals to 0. This is the equation. We I'm recalling this equation when we started about cylindrical coordinate system. When we talk about heat conduction through a cylindrical coordinate system, we talked about it. Now this I am taking into consideration, and now I am deriving this equation. First I will integrate this equation. Once when I integrate this equation once, I will be going to get dt by dr, right, plus dt by dr is equals to minus qr by k plus c1 by r. Okay, r I'll try to write it. This I'll write it as dt by dr, right, plus q dot, this I am writing r dt by dr, q dot by k r is equals to c1. Okay, right. So dt by dr Okay, this is the equation, you know it, right? No, this is not required, right? No, now I'll write it. I'll go step by step. Right. Let me check 1 second, please. Okay. So here the equation is, I'll try to write it here, right? D by dr of r dt by dr into q dot by r is equals to 0. This is the formulation of equation. I forgot here, r is this formulation of equation. This equation I am integrating first. Okay, this equation, when I integrate it first, this is equals to dt by dr is equals to q dot plus, I'll write it, I will not is equals to, I put it, q dot r square by 2, and k is there, and this r which is there, I am bringing it here, is equals to c1 by r. Okay, now this r gets cancelled. Okay, and the range is going to be cylinder, I'm taking it as ri is less than or equals to r is less than or equals to r0. Okay, now this is the case. Okay, I mean to say, this is cylinder, this internal diameter, and this is going to be the thickness. I am considering it r. Okay, this I am considering it. Okay, right, this is ri, this is r0, and this is r, and this is dr. Okay, right, like this I have taken it. Okay, now means this equation is dt by dr plus q dot r by 2k plus c1 by r, right? This I am denoting as equation number 2. Let's take, I denote the equation number 2 now, and again integrating this equation. Then when I integrate again this one, this is equals to, I am bringing this outside, left side, right hand side, this is equals to minus q by 2 as it is there, and k is also there. This r becomes r square by 2. Okay, and c1 r becomes c1 ln r and c2. Okay, this is equation number 3. Means this is equals to minus q r square by 4k plus c1 ln r plus c2. Okay, this is equation number uh, 3 I am denoting as. Now I apply boundary conditions for this. When I apply boundary conditions, right, means when I apply boundary conditions, r is equals to, when r is equals to ri, t is equals to ti. Okay, and when I apply boundary conditions for the exterior wall, r is equals to r0, t is equals to t0. Okay, now means what? First equation, ti is equals to q dot by 4k ri square plus c1 ln ri plus c2, and t0 is equals to q dot by 4k r ro square plus c1 ln ro plus c2, right? When subtract this one, 1 and 2, then c2 is going to get cancelled. Then the equation is going to subtract this equation one, when you subtract this one, c1 ln r0 by ri is equals to t0 minus t0 minus ti plus q dot by 4k into r o square minus r a square and C1 is equals to TO minus TI plus Q dot by 4K into RO square minus RA square, right, divided by ln RO RA, okay, RO RA, and C2 you are going to get from this. C2 is equals to TI plus Q dot by 4K RA square minus T0 minus TI plus Q dot by 4K into RO square minus RA square divided by ln RO by RI into ln RI. Okay, this is you have got it, right? Once you know, then the temperature distribution is going to be, when you substitute the temperature distribution are going to be the values. I'll write it finally. The temperature distributions, I'll write the final equation. What is that? T minus Ti by T0 minus Ti is equals to, final equation I'm writing, ln R by Ri divided by ln R0 by Ri plus Q dot by 4K into RO square minus RI square divided by T0 TO minus Ti into ln R by Ri by ln RO by Ri minus R by Ri whole square minus 1 divided by R0 by Ri whole square minus 1. Okay, this is the temperature distribution. You are going to get it when we consider internal heat radiation also. Okay, and if the radial heat flow Q is given as, QR is given as minus Ka dt by dr, that is equals to QR is given by minus K and A is equals to 2 pi R L dt by dr. Okay, that is equals to minus K 2 pi R L into dt by dr is C1 by R minus Q dot R by 2K. How did you get this? Nothing but, if you see here, this one dt by dr is equals to minus QR by 2K minus C1, right? This one I have substituted here. Okay, all right. C1 is equals to 2 pi L Q dot by 2 R square minus C1K, right? And this is equals to minus 2 pi L into Q dot R square by 2 minus T0 minus Ti plus Q dot by 4K to RO square minus RA square divided by ln R0 by Ri into K, right? This is the equation, right? When there is no heat generation, this is equals to 0. When there is no heat generation, Q dot by 4K is equals to 0. Then the equation would become, for the case of no generation, this becomes that this T0 minus, right? I'll take the cases, right? When there is no heat generation, this is equals to 0. Therefore, T by T minus Ti by T0 minus Ti is equals to ln R by Ri divided by ln R0 by Ra when there is no heat generation. Similarly, heat transfer also, when there is no heat generation, the heat transfer is equals to QR is equals to 2 pi, right? K, L is there, right? This is equals to 0, this is also 0, and this is also 0, right? Therefore, 2 pi KL T0 minus T1 Ti divided by ln R0 by Ra minus is there, right? Or otherwise I can say minus, if it goes 2 pi KL T0 minus Ti divided by ln Ra by R0, right? So this is becomes, when there is no heat generation, it is turned into the first case heat transfer through a radial wall, and that in a one direction. This is going to be this one, okay? One dimensional case. This is the equation is turned out to be, okay? So these are the two cases I have studied. We have tried to discuss today, and the coming class we will try to talk about variation in thermal conductivity in the case of one dimensional heat conduction equations. Then once we solve this one, once we discuss this one, when we'll solve one problem with respect to heat conduction, with respect to heat generation, and we solve one problem with respect to variation in thermal conductivity, and then we'll go to that next topic called as transient state, transient heat conduction equations. We'll go through it. Okay. Thank you. Bye.